Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will learn about the pass transistor logic. So we will see that what is pass transistor logic and what are the advantages and the limitations of this pass transistor logic. And then after, we will see that how to implement the different logic gates with the help of this pass transistor logic. Now this video might be a little longer than the usual videos. So if you want to go to a specific topic, then please use the timestamps which is provided in the description. So in this pass transistor logic, the MOSFETs are used as a switch. So whenever these MOS transistors are in the on condition, then it passes the logic level from the input to the output side. And whenever these transistors are in the off condition, then it will isolate the input from the output side. So in the earlier video of the CMOS logic gates, we have seen that for the NMOS transistor, whenever this gate to source voltage is less than the threshold voltage, then the MOSFET will act as a open switch. And whenever this voltage is more than the threshold voltage, then it will act as a closed switch. Similarly, for the PMOS transistor, whenever the source to gate voltage is less than the threshold voltage, then the transistor will act as a open switch. And whenever this voltage is more than the threshold voltage, then it will act as a closed switch. So in this way, by using this MOS transistor as a switch, it is possible to transfer the logic level from the input to the output side. And using this pass transistor logic, it is possible to build the different logic gates. But first, let us see some of the advantages of this pass transistor logic. So if we implement any logic gates or the logic function using the pass transistors, then we will require the less number of transistors. For example, in case of the CMOS logic, we have seen that for implementing any Boolean logic, we require the equal number of PMOS and the NMOS transistors. So for example, if we take the case of the 2-input NOR gate and the NAND gate, then we will require 2 PMOS and the NMOS transistors. And similarly, in case of the 2-input XOR gate, we will require total 8 transistors. And in that too, we are assuming that both input and its complement are already available. So in general, in the CMOS logic, we will require total 2n number of transistors. But using the pass transistor logic, we can implement the same logic gate or the same logic function with the help of the less number of transistors. For example, this 2-input AND gate can be implemented just by using the 2 transistors. So that is one of the advantage of this pass transistor. The second advantage of this pass transistor is that it is basically a ratio-less. So if you see the CMOS logic circuits, then it uses both PMOS and the NMOS transistors. So as you know, in the PMOS transistors, the main carriers are the holes, while in the NMOS transistors, the main carriers are the electrons. And as we have discussed in the earlier videos, the mobility of the holes and electrons are different. That means if we see the on resistance of this PMOS and the NMOS transistors, then it will be different. So to get the equal rise time and the fall time, the area of the PMOS transistors should be scaled in such a way that we get the equal resistance for both PMOS and the NMOS network. And that scaling also depends on how the transistors are interconnected. So while designing any CMOS logic circuit, we also need to consider the area of the PMOS and the NMOS transistors. On the other hand, if you see this pass transistor logic, then it is basically a ratio-less, because it uses only one type of transistor. And because of that, we do not need to consider all these aspects. And therefore, it is also possible to use the transistors with the minimum sizes. So overall, if you see, then this pass transistor logic requires less area. So these are the basic advantages of the pass transistor logic. But at the same time, it also has few limitations. And the first limitation is the threshold voltage drop. So as you know, both PMOS and the NMOS transistors will not act as a perfect switch. And while passing the logic, there will be some voltage drop across these 2 transistors. For example, the NMOS passes a strong logic 0, but it passes weak logic 1. And in the earlier video of the CMOS logic gate, we have already seen this in the detail. So let's say the threshold voltage for the NMOS transistor is equal to 1 volt. And let's say the input to this NMOS transistor is equal to 5 volt. And the same voltage is also applied as the control input. That means here, this terminal will act as a drain terminal. On the other end will act as a source terminal. So initially, let us assume that the source terminal is at the ground potential. That means initially this VGS is greater than threshold voltage, and therefore this transistor will act as a closed switch, and ideally it should pass this 5 volt to the source terminal. That means the parasitic capacitor at this source terminal will start charging towards this 5 volt. But as soon as the voltage at the source terminal reaches the 4 volt, then this VGS will be same as the threshold voltage. And if the voltage at the source terminal tries to go beyond that, then this voltage VGS will become less than the threshold voltage. And in that condition, this NMOS transistor will get turned off. Therefore, the voltage at the source terminal cannot go beyond this 4 volt. Or in other words, it cannot go beyond this VG minus VT. That means we can say that this NMOS transistor passes weak logic 1. But at the same time, it passes strong logic 0. So in the same condition, now if the voltage at the input is made 0 volt, then this transistor will act as a closed switch. Because in this condition, this node will act as a drain terminal while this node will act as a source terminal. Because the voltage at this node is 4 volt while the input at this node is equal to 0 volt. Therefore, this node will act as a source terminal. And in this condition if you see, then the VGS is equal to 5 volt. So since the VGS is more than the threshold voltage, so this NMOS will act as a closed switch. And now the parasitic capacitor which is charged to the 4 volt will start discharging towards the 0 volt. And eventually the voltage at this node will become 0 volt. So in this way, this NMOS passes a strong logic 0, but it passes weak logic 1. And similarly, the PMOS transistor passes a weak logic 0, but it passes strong logic 1. And in fact, in the previous video of the CMOS logic, we have already seen that in the detail. So if I just look at the NMOS transistor for a moment, then there will be a 1 threshold voltage drop across the transistor for passing the logic 1. And whenever the output of this pass transistor drives the gate terminal of the other transistors, then we will have a threshold voltage drop across each transistor. For example, let's say a threshold voltage for each transistor is equal to 1 volt. So for the first transistor, if the input is equal to 5 volt and the control voltage at the gate terminal is also equal to 5 volt, then the voltage at the source terminal will be equal to VG minus VT, that is equal to 4 volt. And in fact, this output voltage will be the minimum of this VD and the VG minus VT. So in this case, this VG and the VD both are equal. So in this case, this VG minus VT is equal to 4 volt while the VD is equal to 5 volt. Therefore, the voltage at this node will be equal to 4 volt. And this voltage is driving the gate of the another pass transistor. So for the second pass transistor, now the input is equal to 5 volt while the control voltage is equal to 4 volt. So for the second pass transistor if we see, then this VG minus VT is equal to 3 volt while the input voltage is equal to 5 volt. Therefore, its output will be equal to 3 volt. And this voltage will drive the gate terminal of the another pass transistor. So for this third pass transistor, now the gate voltage is equal to 3 volt while the input voltage is equal to 5 volt. And therefore if we see the output at this node, then that is equal to VG minus VT, and that is equal to 2 volt. That means if we see the output of this third pass transistor, then we have a total voltage drop of the 3 threshold voltages. That means the output of the pass transistor should not be used to drive the gate terminal of the another pass transistor. But on the other end, we can connect the multiple pass transistors in the series connection. For example, let's say 3 pass transistors are connected in the series connection. So let's say the threshold voltage drop for the each transistor is equal to 1 volt. Moreover, here the control input at the gate terminal for the each transistor is also equal to 5 volt. So for the first transistor, when the input is equal to 5 volt, then its output will be equal to VG minus VT, that is equal to 4 volt. So for the second pass transistor, the input is equal to 4 volt. On the other hand, if we see the control voltage, then that is equal to 5 volt. That means for the second pass transistor, if we see this VG minus VT, then that is equal to 4 volt. And here, the input is also equal to 4 volt. So in this case, if you see, then the VD as well as the VG minus VT both are same. and therefore over here this output will be equal to 4 volt, and the same will be the input for this third pass transistor. So for the third pass transistor also, this output will be equal to Vg minus Vt, that is equal to 4 volt. So overall if you see, then there will be a voltage drop of the one threshold voltage. But this output voltage may be different if we have a different control input at the gate terminals. For example, if the control input for the second pass transistor is equal to 4 volt, then in that case, the overall output of this circuit will be equal to 3 volt. So let us see why. So for the first pass transistor, the output will still remain 4 volt, that is equal to Vg minus Vt. And this output will be the input for this second pass transistor. Now for the second pass transistor, this Vd is equal to 4 volt, while the Vg minus Vt is equal to 3 volt. So its output will be the minimum of the two values. And in this case, it will be equal to 3 volt. So this 3 volt will be the input for this third pass transistor. Now for the third pass transistor, once again, this Vg minus Vt is equal to 4 volt. On the other hand, this input is equal to 3 volt. And the minimum between these two values is equal to 3 volt. Therefore, the output of this third pass transistor will be equal to 3 volt. So in this way, depending on the control input, we will get the different output voltage. But in short, in the pass transistor, we will have a threshold voltage drop while passing the logic level. So because of this voltage drop, if the output of the pass transistor goes below a certain voltage level, then the next stage may not recognize that input as the logic one. For example, let's say because of the threshold voltage drop, the output of this pass transistor becomes 2 volt. And let's say it is driving an inverter. So in this condition, it is quite possible that the inverter may not recognize that input as the logic one. And due to that, it is quite possible that we will get the wrong output. So that is one of the issues with the pass transistor logic. Of course, at the end of the video, we will also see that how to overcome this issue. But this is one of the issues with the pass transistor. The another issue with the pass transistor is that when we connect multiple such transistors in the series connection, then the overall delay of the circuit will increase. So as you know, when the pass transistor is in the on condition, then it will act as a closed switch. And ideally, its resistance should be equal to 0 ohm. But actually if you see, then it will have some on resistance. Apart from that, each output node of the pass transistor will also have some parasitic capacitance. So effectively, this long chain of the pass transistors will act as a RC network. And because of that, the output node of this long chain will take certain time to reach to the specific voltage level. That means whenever we are using the long chain of the pass transistors, then the overall delay of the circuit will increase. So that is another issue with the pass transistors. Apart from these two issues, the another issue is the sneak path. So if the pass transistor circuit is not designed properly, then it is quite possible that for the some input combinations, there will be a path from VDD to ground. For example, in this circuit, when both A and B inputs are logic 1, then both NMOS transistors will be in the on condition. And because of that, there will be a path from VDD to ground terminal. So in this condition, there will be a large flow of current from VDD to ground terminal. So while designing a pass transistor circuit, we should take care that there is no sneak path in the circuit. Apart from that, while designing this pass transistor circuit, we should always take care that there is a path for charging and discharging this output load capacitor. So like I said, the output node of the pass transistor will also have some load capacitor. And while designing this pass transistor circuit, we should always provide a charging as well as a discharging path for this load capacitor. For example, in this case if you see, whenever both A and B is equal to logic 1, then this transistor will act as a closed switch. And in this condition, this load capacitor will start charging towards the logic 1 level. That means after a certain time, the voltage at this node will be equal to Vg minus Vt. Let's say that is equal to 4 volt. Now in the same condition, now this A is made logic 0. Then this NMOS will act as a open circuit. And in this condition, there is no path for discharging this capacitor. That means in this condition if you see, then the voltage at this capacitor is still equal to 4 volt. That means in this condition, this output node will still act as a logic 1. And if this output node is connected to some other digital circuit, then it will read that input as a logic 1 instead of the logic 0. That means during the design, we should always take care that there is always a path for charging and discharging the capacitor at the output node. And by ensuring that, we can get the correct logical output at the output node. So the same circuit can be modified like this. So now, whenever this A is equal to 0, then this A bar will be equal to 1. So of course, in this condition, since A is equal to 0, so the first transistor will remain in the off condition. But now, through the second pass transistor, this output node will get discharged to the 0 volt. And in this way, every time, we will get the correct logical output. So now the question is, while designing a logic circuit using this pass transistor, how we can ensure that there is no sneak path in the circuit, and at the same time, there is always a charging and discharging path for this load capacitor. So for that, we can take the inspiration from the multiplexer design. So if you see the design of the multiplexer, then in the multiplexer, depending on this control input or the selection line, at any given time, only one of the input will get connected to the output. So for example, in this 2x1 multiplexer, whenever the selection line is equal to logic 0, then this first input will get connected to the output. Similarly, when the selection input is equal to logic 1, then the second input will get connected to the output line. That means at the any given time, only one of the input will be active. And in this way, there will be no snake path in the circuit. And also in the same design, it is possible to ensure that there is always a path for charging and discharging the output load capacitor. So first, let us see how to design a multiplexer circuit using the pass transistor logic. So this is the circuit of the 2x1 multiplexer using the pass transistor logic. So as you can see over here, this control input S and S bar are connected to the gate input of the pass transistors. And here, this D0 and D1 are the two inputs of the multiplexer. So whenever this S is equal to 0, then this S bar will become 1. That means in this condition, this first transistor will be in the on condition, while the second transistor will be in the off condition. Therefore, this D0 output will get connected to the output node. Similarly, when this S is equal to 1, then this S bar will be equal to 0. So in this condition, this first transistor will remain in the off condition, while the second transistor will remain in the on condition. And in this case, this D1 input will get connected to the output node. So in this way, we can design this 2x1 multiplexer with the help of the pass transistors. And similarly, we can also design 4x1 multiplexer. So as you know, in the 4x1 multiplexer, we have total 2 selection lines, that is S0 and the S1. And as you know, for the 2 selection inputs, we have total 4 different input combinations. So here, for the each input combination, the 2 transistors are connected in the series connection. And this D0, D1, D2 and D3 are connected to the each input line. So whenever both S0 and S1 are 0, then this first 2 transistor will be in the on condition. And in that case, this D0 line will get connected to the output node. And similarly, for the different input combinations of these control inputs, only specific line will get connected to the output node. So now if you see over here, then these 2 transistors are connected to the one end of this S1 bar. Similarly over here, these 2 transistors are connected to the one end of this S1 transistor. So instead of using the 2 separate transistors, we can use only single transistor. So this is the circuit of the 4x1 multiplexer. And as you know, using the multiplexer, it is possible to implement any Boolean function or the logic gate. So in the earlier videos of the multiplexer, we have seen that using a multiplexer with the n selection line, it is possible to implement any Boolean function with n plus 1 variables. And we have also seen that how to implement any logic gate using the multiplexer. That means here, we can also implement any 2 input logic gate just by using the 2x1 multiplexer. So very quickly, let us see how to implement the 2 input AND gate using the 2x1 multiplexer. So if you see, then this is the truth table of the AND gate. That means whenever any of the input is 0, then the output of the AND gate is equal to 0. And whenever both inputs are 1, then the output of the AND gate will be equal to 1. So here, to implement this AND gate using the multiplexer, first let us connect the input A to the selection line. So whenever this input A is equal to 0, then irrespective of the value of the B input, this output Y remains 0. So we can say that for the first two input combinations, this output Y remains 0. And as you know, whenever this A input is equal to 0, then this D0 input will get selected. That means here, this D0 input should get connected to the logic 0. Similarly, whenever this A is equal to logic 1, then this output Y is following the B input. That means whenever this B is 0, then the Y is also 0. And whenever this B is 1, then Y is also 1. So we can say that for the last two input combinations, this output Y is same as the B. And as you know, when the selection input is equal to logic 1, then D1 input will get selected. That means in this condition, this D1 input should get connected to the B. So this is how we can implement the two input AND gate using the 2x1 multiplexer. So this is the circuit of the two input AND gate using the pass transistor. So as you can see, this D0 input is connected to the logic 0 while the D1 input is connected to the B input. So whenever this A is 0, then the A bar will be equal to 1. That means in the first two conditions, this output Y will get connected to the logic 0. And similarly, whenever this A is equal to 1, then this A bar will be equal to 0. That means in the last two conditions, the second transistor will remain in the off condition. And now this output Y will follow the B input. That means whenever this B is 0, then the Y is also 0. And whenever this B is equal to 1, then the Y is also 1. So in this way, we can implement the AND gate with the help of the pass transistor logic. So for these two input logic gates, even without using this tabular method also, it is possible to design this pass transistor circuit. So now let us see how to design the two input OR gate using this pass transistor logic. So for the two input OR gate, if A and B are the inputs, then the output Y is equal to A plus B. So here, let us connect this A input to the selection line. That means this input will be equal to A bar, while this input will be equal to A. Or in this multiplexer equation, we will have this A bar dot D0 plus A dot D1. So here, let us connect this D1 input to the logic 1 and this D0 input to the B. So in this condition, we will have this A plus this A bar dot B. And using the distributive law, we can write it as this A plus A bar dot A plus B. And that is equal to A plus B. So in this way, without using the tabular method also, it is possible to build the OR gate. So for that, here this D0 input should get connected to the B input, while this D1 input should get connected to the logic 1. So in this way, if you know a little bit of Boolean algebra, then you can directly implement any logic gate. And of course, using a tabular method also, we will get the same result. So this is the circuit of the two input OR gate using the pass transistor logic. And similarly, we can also implement the two input NAND gate and the NOR gate. So to implement the NAND gate, once again, let us connect this A input to the selection line. That means here, this S bar is equal to A bar, while the S is equal to A. That means in this multiplexer equation, we will have this A bar dot D0 plus A dot D1. Now for the NAND gate, if A and B are the inputs, then its output Y is equal to A dot B whole bar. Or using the De Morgan's law, we can say that is equal to A bar plus B bar. So in this expression, to get this A bar plus B bar, this D0 input should be equal to logic 1, while the D1 input should be equal to B bar. So with that, if you see this expression, then that is equal to this A bar dot 1 plus A dot B bar. So once again, using the distributive law, we can write it as this A bar plus A dot A bar plus B bar, and that is equal to this A bar plus B bar. That means by connecting the D0 input to the logic 1 and the D1 input to the B bar, we can implement this NAND gate. And of course, using the tabular method also, we can get the same result. So for more information, you can check that video, and the link for that video is already given in the description. So likewise, this is the circuit of the NOR gate. So for the two input NOR gate, if A and B are the inputs, then its output Y is equal to A plus B whole bar, or we can say that is equal to this A bar dot B bar. So here, for a change, let us connect the B input to the selection line. That means in the multiplexer equation, this S bar is equal to B bar, while this S is equal to B. So now, to get this A bar dot B bar, this D0 input should get connected to the A bar, while this D1 input should get connected to the 0. And in this way, we will get this A bar dot B bar. So in this way, it is possible to implement the NOR gate using this pass transistor logic. Similarly, we can also implement the 2-input XOR gate and the XNOR gate. So for the XOR gate, this output Y is equal to A bar dot B plus A dot B bar. So if we connect this selection line to the input A, then in this expression, we will have this A bar dot D0 plus A dot D1. So now, to get this expression, this D0 input should get connected to the B input, while this D1 input should get connected to the B bar. And in this way, we can implement this 2-input XOR gate. Similarly, in the XNOR gate, this Y is equal to this A dot B plus A bar dot B bar. So once again, if we connect the A input to the selection line, then over here we will have the A bar, while over here we will have the A input. And in this multiplexer equation, we will have this A bar dot D0 plus A dot D1. So now, to get this expression, this D0 line should get connected to the B bar, while this D1 line should get connected to the B input. So in this way, we can implement the XNOR gate using the pass transistor logic. And in this way, in general, it is possible to implement any logic function using this pass transistor logic. Now earlier I have mentioned that one of the issues with the pass transistor logic is that we will always have a threshold voltage drop across the transistor. That means if we take the case of the NMOS transistors, then whenever it passes a logic 1, then we will have a threshold voltage drop across the transistor. So using a level restoring circuit, it is possible to pull the output voltage to the VDD. So this circuit which is shown over here is the level restoring circuit. So whenever the output of the pass transistor is equal to logic 1, then the output of this inverter will become logic 0. And the same will get applied to this PMOS transistor. So of course at this time, this output Y is equal to VDD minus VT. But now, since the input to this PMOS transistor is equal to logic 0, so it will get turned on and it will act as a short circuit. That means now, this PMOS transistor will pull up the voltage of this node Y to the VDD. And in this way, we will get a strong logic 1 at this node Y. So in this way, using this level restoration circuit, it is possible to get the strong logic 1 at the output node. So that's it for this video, and I hope in this video you understood what is pass transistor logic and what are the advantages and the limitations of this pass transistor logic. And you also understood how to implement different logic gates and the logic functions with the help of this pass transistor logic. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.